everyone. My name is Leighton Barnes, and this talk is going to be about improved information theoretic generalization bounds for distributed and federated learning with model averaging. I'm a postdoctoral research associate at Princeton University, and this is sort of joint work with my colleague Alec Titzo and my advisor Vincent Poor. So we're interested in a generalization error for statistical learning problems. So we're going to have some sort of real valued loss that's a function of both our weights, our model, and our sample. And then the population risk is then the expected value of this loss for some fixed weights where you're averaging over some new unknown sample. Then we also have an empirical risk on a particular data set. This is just the average loss over that data set. And we'll consider an algorithm here is basically a training algorithm for given some n sample data set. You train and get a particular set of weights or a particular model. And we'll be interested in the generalization error, which is then the gap between this population risk for our trained model and the empirical risk on the data set that is the same data set that we use to train our model. The expected generalization error is then the expected value of this generalization error over all training sets. So it's over pi to the n. So there's some information theoretic upper bounds on this generalization error, right? So in general, we care about this generalization error because we want to make sure we have good performance on some new unknown samples so that population loss is low. And we generally train models by doing something like empirical risk minimization. So if you ensure that the gap between the two isn't too big, you ensure good generalization properties, good performance on new unknown samples. And so here, there's some existing literature on how to bound this gap in terms of basically mutual information, some information theoretic concepts. And so the bounds look something like this. If you assume that the loss as a random variable in terms of the independent versions of the random variables W tilde and Z tilde satisfies some sort of tail bound. So here we write that as a upper bound on the cumulant generating function for this random variable. Then you can get an upper bound on the expected generalization error that looks like this. So this is the expected generalization error is upper bounded by the average over the n samples of some function, the psi star inverse, applied to the mutual information between our trained weights and each of the individual training samples. So this psi star inverse function is basically just it is the inverse of the Legendre dual of psi here, where psi is the upper bound on our cumulant gradient or cumulant generating function. Sort of a more maybe well-known version of this theorem is the version due to Zhu and Rodzinski that is a special case of this, where this is a quadratic upper bound because it's a sub-Gaussian random variable, and you end up with a square root dependence here on the mutual information. But what we're actually interested in here at this workshop is a distributed learning setting. So we're assuming that there's k nodes. Each of these k nodes has some sort of n sample data set. And they each train some submodel, W1 through WK. They send all those submodels up to some sort of centralized model aggregation platform, and then you're coming up with a total model, W hat, from all of these submodels. The sort of simplest thing you could imagine is just averaging all of these submodels, and that's what we'll assume for the rest of this talk. Although it's sort of ongoing work for us to work with more complicated model aggregation procedures. So if you try to sort of naively apply the existing information theoretic generalization bounds to this distributed setting, you get something like this. You can sort of first write out just that same theorem, an upper bound on the expected generalization error in terms of sort of the total data set, so all n times k samples. So you have an average of 1 over nk times these mutual informations from each of the individual training samples. You can push the sum over n through because of concavity, and then combine because of the independence of the samples. You can combine them all into some mutual information term that looks like this. So here we have the mutual information between the total aggregate model W hat and the training sample from node k. If we wanted this to give us some insight in terms of like either you treating this mutual information term as like a communication constraint or a privacy constraint, then we might do something like apply the data processing inequality, where this can be written as an average over each of the nodes of the mutual information at each node from the training sample and the individual weights. The problem with this sort of approach is that this bound, we have k different things we're summing over, we're averaging with a 1 over k, so the bound doesn't really decay with the total number of nodes, k, which is bad because we're essentially getting no benefit for the total data set across all of nk training samples. We only get essentially this factor of n decay. So what we'd like in a useful upper bound for these federated learning settings is we'd like some bound that should decay with the number of nodes, capital K, in order to take advantage of the total data set from all k nodes. And then we also, ideally, we would have some terms that look like these mutual information terms, I, WK, SK, which is the mutual information between the submodel at node K and the training set at node K, because these can essentially represent the capacity of the channel that the nodes are communicating over. So it could represent like a communication or local differential privacy constraint for each of the nodes. So we've developed some improved bounds. Here's an example of what they look like. Here's a theorem for general Bregman loss. So it can be any Bregman loss function for any sort of convex function f, and for linear models. So basically in either of these two cases. And we'll have some assumption on the tail of this loss random variable, similar to the previous theorem. But now here we get an upper bound on the expected generalization error that looks like this. So it's a sum over the k nodes of these mutual information terms we're interested in. But the whole thing decays by an extra factor of 1 over k. So we get that it actually decays very strongly and very quickly with the number of nodes and fully takes advantage of the whole data set across all k nodes. So in order to prove this theorem, just a very brief sketch to give you a sense of where that factor of 1 over k comes from. You can write out the expected generalization error with using the sort of leave one out expansion, where it's a difference between the loss for a model here with independent training samples, and then a model here where we've replaced one of the training samples with this same z prime ik. And the key is that these two models, they only differ in terms of the submodel from node k. So using the structure of the Bregman loss function, which I've written out here, we can essentially pull out that factor of 1 over k that sort of multiplies this because we're averaging all of the submodels. And so that ends up giving us this extra factor of k. So here's an example. So if we're, for example, learning the mean of a Gaussian, where our samples are drawn from some Gaussian distribution, and we look at a loss function that is just squared L2 loss between the weights and the samples. So basically, we're trying to get our weights W to be as close as possible to mu, the mean of the Gaussian. So an obvious algorithm would be for each node to sort of average all of their samples together and then transmit those weights, those submodels, up to the aggregation platform that would then average all of them to get a total estimate for the mean. What's nice about this example is you can explicitly write out the mutual information terms. So you can compute these mutual information terms. You can get an explicit bound on this psi star inverse. And so applying the existing bounds, we get that the expected generalization error is upper bounded by an order 1 over square root of nk factor. However, for this specific algorithm and distribution, you can just compute what exactly is that generalization error. And it looks like factor 1 over nk. So the existing upper bounds don't give the correct dependence on n or k. But applying our new information theoretic upper bound, we get essentially an order 1 over k times the square root of n upper bound. So we get the correct dependence on the number of nodes, and it decays as it should. However, you're stuck with this 1 over square root of n factor. There's probably no way to improve that if you want your bound to apply for a large variety of algorithms and distributions, because in some cases that is the tight dependence on n. And so if you're interested in sort of nonlinear models or more complicated loss functions, you can prove similar sorts of results, for example, for Lipschitz continuous loss functions. So here's an example of one of those results. The assumptions get somewhat more complicated, and so does the upper bound. However, the moral of the story is you can still recover this 1 over k total decay factor, even in more complicated nonlinear situations. So feel free to stop by and ask more questions if you want to talk about this theoretical work. Thanks a lot for your attention.